All right there, chem scholars. Today I have to get into the idea of enthalpy so we can take our calorimetry a little bit further. So you may have been wondering why heat is an H, and it's because enthalpy is H. Now, why is enthalpy H? Why isn't it E? Because E is used for energy or internal energy specific, yada, yada, yada. Okay, just go with it, all right? We've talked about potential energy a bit so far. In chemistry, when we talk about potential energy, it tends to be this discussion of what we call enthalpy. Enthalpy is the chemical potential energy that is stored. We tend to refer to it as stored heat content, but of course heat can't really be stored. But it is related to heat because as heat comes into a system, it tends to increase the enthalpy, and if heat goes out, that means it decreases the enthalpy. So if the pressure is constant, heat and enthalpy really are the same thing. Well, the change in enthalpy and heat are the same thing. Enthalpy is related to energy and pressure and volume. We're not going to get into that. That just came with the diagram there, so don't worry about that thing. Okay, so just keep in mind that we're talking about potential energy here. Okay. Very often we're going to talk about the heat of a reaction or the heat of a process. Okay, that's delta H, or the change in enthalpy. The change in enthalpy, though, has to also have an effect on the surroundings. For example, if a reaction is absorbing energy, well, where's that energy coming from? It's coming from the surroundings. So the surroundings are losing energy so that the system can gain energy. And vice versa. Obviously, if a reaction is giving off energy, where's that energy going to? It's going to the surroundings. So that means that if the system is losing energy, then the surroundings have to be gaining energy. So the amount of enthalpy in a system and its surroundings are always going to be, the change in enthalpy for a system and its surroundings are always going to be equal, but opposite. All right, so that's going to be important when we do calorimetry, because a lot of time when we look at a chemical reaction, we run a reaction and it causes water to heat up. So we think, well, the temperature rose, so that means that this system must be endothermic. But that's the surroundings. That's the water that we're measuring or whatever else, not the actual thing that produced the heat, which was the system. So the system was exothermic, causing the water to absorb heat to be endothermic. There's going to be this opposite involved in so much of what we do here. So be aware of it. So we've used the term endothermic a little bit before. We said endothermic is a process that absorbs heat. But why does it absorb heat? Well, a process is endothermic when bonds or intermolecular forces, IMFs, are being broken. Okay? That's because it takes energy to break these electrical attractions. And so energy goes in, and that's where endothermy comes into play. For example, if I'm boiling water, okay, I'm going to put heat in to break apart the intermolecular forces holding that liquid together to convert it into a gas that's going to move out on its own. Likewise, if I'm talking about a reaction with, I'm trying to do a decomposition reaction, like lithium sulfide, to break it into lithium and sulfur, well, now I have ionic bonds that have to be broken, and it takes energy to do that. It's an endothermic process. Okay, so remember that endothermic is when bonds or IMFs are being broken. Obviously, the reverse is true then. If we're talking about making bonds or forming bonds or IMFs, then it's going to be exothermic. That one doesn't seem as intuitive, but again, opposites, right? I mean, if energy going in breaks bonds, then it should make sense that making bonds releases energy. Why? Because it makes things more stable. Okay, bonds form to increase stability. When we talk about stability, that means something is lower in energy, and very specifically, we're going to talk about being lower in enthalpy. Okay, so whenever we talk about something being more stable, that means that it is lower in enthalpy. Anyway, so as bonds are formed or intermolecular forces are formed, we're going to give off energy as it becomes more stable. So, for example, going to water, if I freeze the water, Okay, I have to calm it down. I'm going to make it more stable because the water molecules have a lot of random motions, but ice really doesn't. So I'm calming it down. I'm lowering its enthalpy. That means it's going to be exothermic. It's got to give off that extra energy. And the reverse, before we talked about decomposition. So now if we talk about synthesis reaction, well, if I put magnesium and sulfur together, sulfur is going to pull on electrons from magnesium, causing them to form a bond, which is an exothermic process. Okay, so we have a little bit of a picture there of endo and exothermic. Okay, and again, we have to keep in mind that what's going on with the system is opposite for surroundings. If the ice is absorbing heat in order to break its intermolecular forces and start to melt, well, then that heat had to come from the surroundings. Surroundings has to be losing heat. Okay, if I'm, cooking outside on my grill and my grill is giving off heat, well, that means the air, the system around it, the environment is got to be absorbing the heat. Okay, so if the combustion reaction of the propane is giving off heat, it's exothermic, then the surroundings have to be absorbing heat, and that's going to be endothermic. For example, here's two different types of solutions that are not too uncommon. One is a cold pack, one's a hot pack, and they're both made by solution process. So you might think, well, wait, if they're both solution, why is one endo, one exo? It's just because of the different changes in energy going on that take place between the two things. The one case on the left, the cold pack, we have ammonium nitrate, and as it dissolves, okay, the process absorbs more heat than it would release. Whereas on the other side, we have this sodium acetate supersaturated solution. And so as that starts to precipitate out, that's an exothermic process. But let's talk about why they're different a little bit more. Okay, we have to recognize that there's three things that go on when we make a solution. First off, I have to take the solute intermolecular forces and break them up. I have to take the solvent-solvent intermolecular forces and break them up. I have to then take the solute and solvent and make new IMFs between them. So I have to connect those things together. So two things are being broken. Well, we said those are endothermic, so the first two steps are endothermic. But the third step is where we're making IMFs, so that would be exothermic. So you might say, well, if two of them are endothermic, one's exothermic, that should mean that it's endothermic. But it depends on the amount of energy that's going to be released in this last step, okay? In the case of that precipitation of sodium acetate, it releases a lot more energy than is needed to break up these things, the IMFs, and so we're going to have an overall exothermic process. Whereas for the ammonium nitrate in the cold pack, obviously it releases very little heat, so more heat is going in than is coming out, and so overall it is endothermic, it is absorbing heat. All right, so it's not always one simple thing. Sometimes we have to look at the whole process. So the lattice energy, the formation of sodium fluoride, is shown below. A combination of steps is proposed to be involved in determining the enthalpy of this reaction. Which statement provides the best answer and justification for the energies of these steps? So we have this overall reaction, and we have these four processes listed there. And we're told that delta H for this reaction is negative 904. Negative means it's losing heat. That means it's exothermic. Okay, so we know that overall it's exothermic. That's not really what the question is asking. So now it's looking at these four processes and saying which ones are endo or exothermic. So first thing it says is process one is endothermic. Well, let's see. If I go from a solid to a gas, I have to break intermolecular forces, okay? And so that would be an endothermic process. All right, that seems pretty reasonable. Let's see, process one is endothermic because energy is released. Whoa, endothermic does not mean energy is released. That statement is not completely correct. Let's go on to step two. Process two is exothermic because sodium has a low electronegativity, All right, well, let's look at this. We are definitely breaking an electron off. We're breaking an electrical attraction, okay? Breaking should be an endothermic process, not exo. Got to disagree with number 2 there. All right, process 3 is endothermic because energy is required to break a bond. Well, let's see, we're going from fluorine to 2 fluorine atoms. We are breaking a bond, and it would be endothermic. So C is definitely correct, but let's talk about D anyway. Process 4 is exothermic. Well, let's see. If I make a bond, yes, it would be exothermic because fluorine has a high electronegativity. Well, that has nothing to do with the process, and actually this reaction is nothing to do with electronegativity. It's electron affinity. So no, the D is just not quite right. And in case you didn't follow me, you could pause this and look at the reasoning here as I break it down, but C is the correct answer. All right, let's talk about another scenario. So we have this chemical called urea. It's dissolved in water. A decrease in temperature is measured. The student makes the following conclusion. Do you agree or disagree with the student's conclusion? The decrease in temperature indicates the system is losing heat, suggesting that the dissolving process is exothermic as heat is released when urea hydrogen bonds with water. Okay, think about this for a moment. Okay, try and unpack it. And let's talk about it. Student is definitely wrong. Okay? If the solution is getting colder, that means that the solvation process is absorbing heat, and thus it is an endothermic process. Yes, hydrogen bonds are being broken, as are the dipole-dipole attractions in urea, but that does not guarantee that the process is endothermic or exothermic. Remember those hot and cold packs we talked about? Just because 1 or 2 steps are endothermic doesn't mean the whole thing is endothermic, or just because 1 step is exothermic does not mean that the whole thing is exothermic. Okay? So you got to be careful with the wording. Think about the process a little bit. Okay? Sometimes we have to think about what's going on in the overall process. So far, okay? Yeah. All right, let's keep going. So what we have here is called an energy profile or an enthalpy diagram, potential energy diagram. What we see is a diagram that's showing the relationship of the reactants, which would be this horizontal line on the left, and the products, which I guess would be, technically there should be a horizontal line here on the right, and the fact that we have some change going on in between. Well, right now we're not worried about the in-between part. We're just comparing reactants and products. Okay? Enthalpy is what we call a state function. A state function means we don't care what happens in between. We only care about our final position and our initial position. Okay? Our products minus our reactants. It does not matter what happens in between. That's what we were talking about in the previous examples, where we have to look at the overall process. All that matters is where we start and where we end, and what happens in between is part of it, yes, but we really are basing our answer off of just initial and final states. Okay. Some things like work is a path function. For example, if I'm trying to move my desk from here to the back corner of the room, the least amount of work I could do is by going in a straight line. But if I decide to push it around this and go this way and this way, I'm going to spend a lot more energy. I'm using a lot more of my energy to do work. Okay, and that's because I took a bad path. Okay, so sometimes the in-between matters. With enthalpy, it is not going to matter. We're going to be just talking about state functions, so we only need to know what our initial states are, what our final. So let's look at that a little bit more. Okay, we see that in this diagram that the reactants start with 150, we'll say, joules of potential energy, and the products end with 50 joules of energy. So we're clearly starting with more energy than we're ending with. Okay, so we have to give off energy to go from 150 down to 50, which means that this diagram is showing an exothermic process. And if we actually calculated out delta H, now remember a moment ago I said delta H could be done from products minus reactants. So if I take 50 minus 150, I get negative 100. I'm getting a negative number because it's exothermic. The system is losing heat. The surroundings, the environment, would be gaining the heat, but that's not what we're talking about right now. This diagram is just about whatever system we're talking about, what reactants, what products we're starting with. Conversely, here's a diagram where we see that the reactants start at a lower enthalpy than the products. Okay, so obviously to go from 100 and end at 300 means somewhere along the way we had to gain energy. We had to absorb energy from the surroundings. Okay, so this is an endothermic process, and if I were to calculate out delta H, I do my products, 300 minus my reactants, 100. 300 minus 100 is 200 joules, I assume, maybe kilojoules. I don't know, should have labeled it. Point being that this is endothermic. We have a positive value for delta H. Okay, so it does say kilojoules down here. Okay, that's random. Okay, put that somewhere else. I don't know. Okay, so it was supposed to be kilojoules. Go figure. All right. All right, let's try a question relating to this idea then. Which of the following best describes the change occurring in the reaction represented by the energy profile to the left? Okay, 25 kilojoules of heat is transferred from the system, and the products are less stable than the reactants. All right, so there's two things obviously that are going on in this question. First of all, we have to understand whether energy is transferred from the system or energy is transferred into the system. So this is what type of process. If we start with low energy and end with a higher enthalpy, well, that means energy had to go in. That means it's endothermic, okay? And so energy's got to be transferred into the system. So we get anything that says from, like the first and third option, have to go out the window, not possible. Then we have to talk about stability. Well, stability means lower in energy or lower in enthalpy. So obviously the reactants are lower than the products. So the reactants are more stable than the products. Okay, so now we have to process that in here. So we want to talk about energy going into and the fact that the products are less stable than the reactants. I kind of like that choice right there. An experiment was performed to determine the energy changes in a chemical reaction and a graph of temperature versus time. Okay, so this is not an energy profile diagram like we just saw. This is just a graph of temperature and time. So we see that we start at one temperature and then eventually we end at another temperature. Okay, is the reaction endothermic or exothermic? Okay, so we have to be real careful here when we talk about this. Part A. Okay, as we see that the temperature is rising, which means that heat had to go into what we're measuring. Okay, but we're measuring a reaction. Okay, so what we're measuring when we measure the temperature, we're measuring the temperature of the surroundings. You can't really stick a thermometer into the reaction. We can only measure it as what happens as a result of it. Okay, so really this graph is the graph of the surroundings. And we see that the surroundings are absorbing heat to go from 20 degrees or almost 20 to almost 40. So that means that the surroundings are absorbing heat. The reaction is giving off heat. So the reaction is exothermic. Now, Part B, a student states that the energy required to break the bonds in the reaction is less than the energy released when the bonds form in the products. Do you agree or disagree? All right, we just said a moment ago that the reaction is exothermic. We said earlier that energy used for breaking bonds is endothermic and energy for making bonds is exothermic. So we need more energy to come out than is going in. So that means that there should be less energy for breaking bonds than for making bonds. I would agree with this student. And then it says to sketch an energy profile for the reaction. Okay, so what do we know? We know that we're going to be starting with, we know it's an exothermic process, so that means that the reactants have to start with a higher enthalpy than the products. Okay. So we should end up with something kind of like this. Now again, what that hill is in between, we don't care about yet. That's something we'll get to in the next unit. All that matters is that we know that the reactants started higher than the products. Anything else is irrelevant. All right, so let's try and tie this back now to the idea of calorimetry a little bit. When we talk about phase changes, okay, phase changes mean that we are changing intermolecular forces, okay? Solids to liquids, well, solid is really locked in, strong intermolecular forces. Liquids have looser intermolecular forces, allowing them to be a little fluid. And gases, of course, have almost no intermolecular forces, so they have to be completely gone. So if I'm going from solid to liquid, which is melting, or for some strange reason, people like to call that fusion in this topic. I don't know why, okay? Or if I'm talking about going from a liquid to a gas, which we call vaporization or boiling or evaporation. And if we go directly from solid to gas, which is called sublimation, those would all be endothermic processes because we are breaking or weakening at least the intermolecular forces. So obviously the reverse situation would be exothermic. When you are freezing something, if you put water in your freezer and it comes out as ice, what the freezer does is it pulls heat away from it because the reaction is giving off heat and the freezer is just taking it away so that it can dispose of it out the back of the freezer. Okay, so freezing is an exothermic process. Condensation is an exothermic process. Okay, when you're going from steam, which is hot, to the water cooling and forming on, on a cool surface like a mirror or tile or whatever else. Okay, that is condensation forming because it gave off energy. It was exothermic. And deposition, of course, going from a gas all the way down to a solid would definitely require the loss of energy. Okay, so again, it's all about heat flow, okay, whether we're breaking IMFs or making IMFs, okay. I'm not going to go into that too much further. You can look at that diagram more if you like. We've talked about heating curves already, okay, and we've talked about the idea that, the flat or horizontal lines are where phase changes are going on. So now we can tie that into what we just talked about, that means that we are talking about a change in enthalpy, okay? So previously, we were doing the calorimetry and we just talked about specific heat capacity, and that related to heating up one substance. So heating up a solid or heating a liquid or heating a gas, those would all be situations where we talk about Q equals MC delta T because there is a change in temperature, okay, and there is a specific heat capacity because we have one substance in one particular phase, okay? But when we talk about phase changes, that's a change in potential energy or a change in enthalpy. All right, so now we're going to introduce another relationship there, okay? Q equals M times delta H. Now, yes, we could do it with moles, okay? Yeah, I might throw a little bit of that out there. But you notice, for example, these, what are called latent heats. Latent heat is another term for potential energy, okay? So we're still talking about enthalpy, really. That's just the way this table labeled it, okay? You'll see that, for example, the heat of fusion or the heat of melting of ice to water is 334 joules per gram, okay? So if I know how many grams it is, I know how much heat it will take. The heat of vaporization, or the heat to boil the water into a gas, is 2258 joules per gram. Okay, so keep in mind, fusion again means melting, vaporization means boiling. Water freezes at 0 degrees or melts at 0 degrees. water boils at 100 degrees or condenses at 100 degrees. Okay, and then you see some other substances there as well. Okay, so there's really two types of things that we can look at when we talk about calorimetry, not just MC delta T, but we could also talk about phase changes happening as well. All right, so let's take a deeper dive into that. All right, this we talked about already. I'm not going to go back to it. Talked about this already. All right, this is what I want to get into. All right, so let's talk about a situation where we have 200 grams of ice at negative 50 degrees, and we want to convert it completely to steam at 130 degrees Celsius. So let's figure out what we have to do. So what we really need to do first is think about this diagram. I'm down here at negative 50 degrees, and we want to get up here at 130. I look at this and I see 1, 2, 3, 4, 5 different lines. So that means I got to talk about 5 different processes in this question. Okay? So we're starting with ice at 200 grams of ice at negative 50 degrees. But I know that ice is going to melt when it hits 0 degrees Celsius. All right, so the first step we're going to do is to heat the water to its melting point. Heat the ice. So we know the mass was 200 grams. The specific heat of ice happens to be 2.02 joules per gram Celsius degree or Kelvin. And the change in temperature is from negative 50 degrees to 0 degrees. Now you may be wondering, why am I saying Kelvin and then Celsius? Because for a change in temperature, it doesn't make a difference. The change from negative 50 to 0 happens to be 50 degrees. If I convert this to Kelvin, it's 223. If I convert this to Kelvin, it's 273. And 273 minus 223 is 50 Kelvin. So the temperature temperature change could be in Celsius or Kelvin. They're interchangeable whenever it's a delta T. So where the last unit we had to talk about temperatures and we had to stick to Kelvin, here it's a change in temperature, it doesn't matter. So the first step in the process, just to heat up the ice, would take 200 grams times the specific heat capacity, 2.02, times the change in temperature, 50 Kelvin. We would get 20,200 joules. That's just the first step. Now we're at the melting point, so the next thing to do would be to melt it. So that's M times delta H of fusion. Well, the mass is 200 grams, and the heat of fusion I showed you on the chart just before was 334 joules per gram. And so that means that we take 200 times 334 and we get 66,800 joules. So now we've melted the ice. What do we have? We have water. At what temperature? 0. Now I can heat the water up until it gets to its boiling point, which is 100. So we're going to now go from 0 to 100 degrees. Okay, so now we go back to MC delta T because we're changing the temperature again. And the mass is still going to be 200, but now because it's water, the specific heat is 4.18. The change in temperature from 0 to 100 is 100 degrees, and so it takes 83,600 joules. So again, let me go back to this diagram. We did the first step, heating up the solid, then we melted it. Now we heated up the liquid. So now we're coming up to here to another phase change. Okay, so now the next step is going to be to boil the water or vaporize the water. So the heat of vaporization is 2256. I rounded to 2260 here. That was on that chart I showed you a little while ago. And so when we multiply it out, we get around 452,000 joules. Notice how much more heat is here than anywhere else, because we're talking about boiling. When we boil, remember, we assume, ideally, that gases have no intermolecular forces. So we have to completely obliterate all of these intermolecular forces. So a lot of energy's got to go in to break those forces. So that gets us now, we've boiled the water, we have steam, but the steam is at 100 degrees. Remember that phase changes don't involve a change in temperature. So we were at 100, we're still at 100. Now we got to go up the rest of the way. All right, so finally we want to go from 100 degrees to 130 degrees. So we go back to MC delta T because we're changing temperature, but now we have to look up the specific heat capacity of steam, which is around 2.08 joules per gram Kelvin. So I take the mass times the specific heat times the change in temperature, and now we get 12,480 joules. Okay, but the question, now that we're at the final temperature, we have to keep in mind that temperature said how much total energy is needed. So now we got to add up all the steps. So we take each individual step from heating the solid, melting it, heating the water, boiling it, heating up the steam. When we add that all up, we get around 635,000 joules, or 635 kilojoules. Sometimes I will ask for kilojoules just because I don't want to have to deal with those extra digits, and it's easier from a sig fig point of view if we do that anyway. All right, let's look at two quick examples, and then I'm going to end this video. You can always go back and fill in as you need to. Gallium can be purified by melting. How much energy is required to melt 2 moles of gallium, originally at 293 Kelvin? All right, so we're talking about melting. Melting, for whatever strange reason, is fusion. Okay, notice that the heat of fusion here is kilojoules per mole. Well, that's convenient because we have 2 moles. So I just have to multiply 2 times 5.59 to get the answer, which would be around 11.8, 11.7, and yada yada. Okay. Silly me. I didn't read the question completely. Bad me. Notice that it said, let me go back here. It melts at 303 Kelvin. We were at 293 Kelvin. So there's actually 2 steps to this process, not 1. I got ahead of myself. Let me backtrack. If I could erase this, I would, but I can't. I'm not re-recording the whole thing, so bear with me. Okay, so the first thing we have to do is heat up the solid 10 degrees, and then we can melt it. Okay, so really there's 2 steps. One involves heating it up. So we notice the 10 degrees times the specific heat, but the specific heat's in moles, not grams. So I used moles here just to keep the units together. And then we melted it or fused it. So that's where the 11.18 comes into play. And now when I combine these two, now keep in mind this is in joules, this is in kilojoules, so I got to make them both kilojoules. We end up with around 11.7 kilojoules overall. Okay. My bad on that. Don't worry about it. We're not going to do as much with moles anyway, but I wanted you to see it now. One more question. Let's go to it. Why is the heat of vaporization so much larger than the heat of fusion? All right, so the heat of vaporization is 256 kilojoules per mole, where the heat of fusion is only 5.59 kilojoules per mole. Well, I answered this one already if you were paying attention. Okay, we said that when a solid is melted into a liquid, there are still IMFs. So when we're going from solid to liquid, I'm weakening the IMFs. But when I go from a liquid to a gas, well, now I'm, like I said before, basically obliterating those intermolecular forces. And so a lot more energy is needed to do that. Okay, so we have to be aware of that idea. All right, I think that's more than enough for one class. You've been good, I imagine. Oh, maybe you're not. I don't know. But sorry to do it this way, but you know, things happen. We got to roll with it. Have a good day, guys. I'll talk to you online tomorrow.